Hello there. In this video, we're going to be using the unit step function to help us analyze circuits with time-dependent sources. So, just a quick overview over the unit step function. The unit step function has a form of this, u of t minus t initial, where t initial is the time where you want this this function to jump to 1. So in this case, we have our t initial to be 0 seconds, at 0 seconds. So when anything greater than 0 seconds, this function will jump to 1. Anything less than 0, this t initial, has a value of 0. So this function will be 0. Now this unit step function, we use it when we have time-dependent sources. Say that this voltage source and this 3 ohm resistor, say we want to apply a 5 volt across this 3 ohm resistor, but we want to apply it at a specific time, at a specific period of time. We don't want it to apply it too early. We don't want to apply it too late. So what we use is we use this unit step function to indicate when this function should jump up to this value, or when it should be off. Okay, let's say that we want to apply a 1 volt voltage source across this 3 ohm resistor, but we want to apply it at 5 seconds. 5 seconds. So in this graph, say 5 seconds would be our t initial. And we want to apply 1 volt. So we're applying 1 volt. So the equation will look something like this. U of t minus 5, the time when you want it to jump to a value of 1. And we want to apply it at, so we want to apply 1 volt. So what this equation is saying is that this u of t, anything greater than 5, this value, this function would jump to 1. Anything less than 5 is 0. So if we have more than one step function, let's say we have plus 3u of t minus 4. No, sorry, minus 6. What the graph will look like is that so what we're doing is that after 5 seconds, we're applying 1 volt, and then at 6 seconds, after 6 seconds, let's say this is 6, we're going to apply another 3 volts. So this is going to jump from here to here. We're going to apply another 3. Let's say that's 3. So it's going to apply another 3 volts. That's what's happening in our unit step function. Now, notice that this is for positive time. We do u of t minus t naught. And for negative time, we use u of t plus t naught. Now that's an important difference that you must remember when you're using the unit step function. Now let's look at a circuit with time-dependent sources, and we'll take a look at how we use our unit step function to help us analyze that circuit. Okay, here we are. We have a circuit that is excited by a current source and a voltage source, and assume that the switch is in position A. So it's this circuit, this only left circuit, for a long time. It's been in this position for a long time, and then at t equals 0, the switch goes to position B, and we're just analyzing the right side of a circuit. So we want to find VO, the voltage across this capacitor, for t greater than or equal to 0. Now what we need to know is the initial voltage across this capacitor before it goes to position B at t equals 0. So we're going to use the general solution to natural and step responses, where we need to find our final voltage. This is where we find voltage across capacitors, and our initial voltage and our tau. And in this case, we have simply an RC circuit. So tau is our Thevenin's times your capacitance. Okay. Well, first step is to find your initial voltage. Initial voltage. So initial voltage is when it's in position A, when the switch is in position A. So let's redraw this circuit. So we have 4 amps, 3 ohm resistor, and this capacitor, 0.5 farad capacitor. If you recognize that under steady state, when this has been in this position, when this capacitor has been in this position for a long time, this capacitor pops open. That's the nature of capacitors when it's been under a constant independent source, constant sources. It pops open, and we have an open circuit right here. And what we're finding is the initial voltage. So the voltage here at A and the voltage here at B. The voltage here at A and at B is the same voltage across this 3 ohm resistor. So say that V, voltage across capacitor for T, for less than 0, our initial voltage is equal to negative 4 amps times 3 ohms. The reason it's negative because you must recognize the polarity. This is minus, this is plus. Usually you have a current source in this direction, and that's when this value would be positive 4. But since the current arrow is pointing downwards, it is negative 4. So we have 4 times 3 is 12 times negative 1 is negative 12. Negative 12 volts as our initial voltage. Now let's find our final voltage when the switch is in position B. Now when it's in position B, notice that this time-dependent voltage source would activate at when it's T1, and then it would activate at T2. The time is 1 times 2. So the simplest way is to replace this a time-dependent source and replace it by a 1 volt voltage source. If it was a current source, replace it by a 1 amp current source. So let's do that. So let's redraw our circuit. We have our capacitor, our 2 ohm resistor, and 4 ohm resistor. 4 ohm resistor, and we're replacing our time-dependent voltage source by a 1 volt voltage source to make our life a bit simpler when we're analyzing the circuit. So it's in position B. Now it's in position B for a long time, meaning it will stay in position B after that. So this capacitor pops open. Trick to remember, something to remember is that under steady state, capacitors pop open, inductors short. And we want to find the voltage at A and B. And notice there's no current through this 2 ohm resistor, so there's no voltage across this resistor. So the voltage across A and B is the same voltage across this 4 ohm resistor. And if we use the voltage divider rule, we can find the voltage across A and B. So when time goes to infinity, we have this capacitor that pops open. We're finding the voltage across this 4 ohm resistor, which is 4 ohms divided by the equivalent resistance. It goes from 1 volt and goes 4 ohms and 4 ohms. There's no current going through here or voltage. times the voltage supplied, 1 volts, and we have 1/2 volts. So this voltage, when t greater than 0, is 1/2 volt.